Hi guys, I'm recording this video because we will miss the Monday class due to on the observance of Memorial Day, which is the national holiday in Korea. Uh, so, so we are running to the end of this semester. So please keep studying hard, and then I hope you. I hope you to be prepared for the final exam, then so you can get the good scores in the final exam. So we have only 3 classes until the end of this course, including actually this today's class. So please keep studying hard, right? So actually, in the previous class, we learned about the multi-level cache hierarchy. So like the memory hierarchy, cache also has multi-levels of cache hierarchy. So which means that in the level 1 cache, so the processor provide the fast cache, but the size of the cache is small. So I repeatedly said that if the size of memory is increased, then the latency and also the performance. The latency is increased, so which means that the performance of memory is decreased. So also it's the same to the cache memories. So which means that if we use the very large single level cache, then the performance of this cache will be low. So which means that the hit time is long, so which means that the access latency is the basic access latency is high. But if the hit time is high, so which means that we can calculate the AMAT, which is the average memory access time, like the hit time plus miss rate multiplied by miss penalty, right? So hit time is also very critical for the performance of cache, also for memory hierarchy. So which means that we need to use the high performance cache for the level 1 cache. So which means that the level 1 cache size is small, but the latency, the access latency of the level 1 cache is low. So if this level 1 cache is directly connected to the main memory, so which is very slow, so then if the access to this level 1 cache is missed, then we need to access the main memory, so which is very slow. So which means that the miss penalty is high. So which means the AMAT is also increased. So we use multi-level cache hierarchy. So which means that after the level 1 cache, so actually in the low level of the level 1 cache, this is the next level of the low level 1 cache, then we have unified. So which means that in the level 1 cache, we have 2 different kinds of caches, like the instruction cache and data cache. But in the level 2, we use unified cache. Also, the size of the level 2 is larger than the size of level 1 cache. So which means that the main purpose of using level 1 cache is decreasing the miss rate. Okay. So also we using this example, we calculate the effective CPI of the single level cache. Also, we also calculate the effective CPI if we use the multi-level caches. Okay. So and then this example shows that we can improve the performance of a processor if we use multi-level cache hierarchy. Okay. Also, we learned how the algorithm and how the data is handled by software influences the performance of a computer system. But we analyzed this performance of a software in the aspect of cache hierarchy. Okay, so this is a very popular example of the that shows the influence, the performance influences from cache hierarchy. So which means that if we use some dummy algorithm, such as the simple matrix multiplication algorithm, then if the size of this matrices is increased, then the whole elements of these matrices cannot be stored in the small cache size. Okay, so we can apply the enhanced matrix multiplication algorithm that utilize the submatrices which have smaller sizes. So actually we compare the performance of the matrix multiplication by some algorithms, so which considering the size of cache memories. Then with the unoptimized version, the performance of this matrix multiplication is decreased because the entire elements of matrices are not stored in the cache memories. But if we use the enhanced algorithm, so if we use the smaller submatrices for matrix multiplication, then the performance is slightly decreased, but this performance down is not as high as the unoptimized version. Okay, so and then this result shows that we need to use the fancy algorithm that can utilize the cache hierarchy, right? So which means that which means the software engineers or software programmers also needs the knowledge on computer architecture, right? So actually the performance is the very critical factor of the computer system. Okay, and then so in this class, so we will actually in the previous class we will also learn about the 3 C's of caches, right? What are 3 C's? So 3 C's of cache represent the causes of cache misses. Then the first one is the compulsory misses, so which is also called the cold misses. And then the second one is capacity misses. So these misses are caused by limited size of cache memories. Also, the third misses are conflict misses, right? So which means that if we use the set associative caches, or if we use the direct mapped cache, then the miss rate of these set associative caches or direct mapped cache is higher than the miss rate of fully associated cache, right? So which means that because of limited associativity in cache, the cache performance can be degraded. So which means that the cache miss rate is increased. So conflict miss means that which means the misses caused by limited associativity in cache, right? Okay. So and then now, so in this class, we will learn about the virtual memory. So which is a little bit. So this topic is a somewhat totally different topic of the cache hierarchy. So in this virtual memory topic, so we will learn how actually applications access main memory space. Okay, so let's think about the terminology virtual. So what does that mean? What does virtual mean in in the normal normal world, like in the real world. So what does that mean? This virtual means that it's just a fake, okay, or it's imaginary, and then not real. So, and then the opposite concept of the virtual means physical in computer systems. So physical means that it's real. Then what does that mean? Then what is virtual memory? So virtual memory is, so I said it's not real. So which means that we can say that this memory is not real memory. So in this chapter, in the memory hierarchy chapter, so we learned about the memory hierarchy. And then we actually, in a real computer systems, in the real computer hardware, we use real memory components such as the cache memories, also is like SRAM. So we use the main memory, which we use DRAM memories for main memory of the computer system. Also, we can use hard disk drives or solid state drive. So which means that so we can use the magnetic disk, or we can use flash memories as the media of the disk is HDD or SSD. So it's real memory. What does that mean? It's a virtual memory. So in order to understand the virtual memory, then we need to also consider abstractions in computer systems. So then what is an abstraction? Actually, we learned the concept of abstractions in the first class of this course. Then, so think like this. So when we write the code, do you consider what the size of the memory and then how the number of cores in your computer systems? Actually, no, because when we write the code, we just write the code based on, so we do not consider what the hardware of the target computer systems when we write a code. So we do not consider about some limited size of the main memory. So we do not consider how the variables are assigned in the main memories. Okay, so these are the tasks of operating systems. So virtual memory just means that actually the operating system and the computer hardware just provides that we provide very large memory and then limited resources of computing cores. So what does that mean? So for example, we can access a variable with the load instruction like x1, 0, x2. So this is the address, and then with this address, then we can access the data in the main memory with the load instruction. So this is the load instruction of application 1. Then another load instruction. So this is the load instruction from application 2. Then this load instruction can also access the main memory. Then what is this address? So actually we can think that until now, we consider that this address is the address of target data in main memory, right? So actually, so which means that we use the DRAM as the main memory. So which means that let us assume that this address is the 0x0010. So which means that we can we can think that with this address, this load instruction just access the data in address 0x0010. Okay, and then this address is determined when our program code is compiled by compiler. But think like this: this compiler does not know the target, the configuration of target computer system. So which means that, oh, the same compiled binary can be executed on the very low level computer system, such as the computer system that use the Intel Celeron processors. Also, the same binary can be executed on the very powerful computer systems, such as the server computer systems that use Intel Xeon processors. So actually, so which means that the environment are different. So which means that the configurations of a processor, also the size of the memory, also are also different for different computer systems. But when our program code is compiled by a compiler, then this compiler does not know about the configurations of the target computer system. So which means that the number of cores or also the performance of the processors, also the compiler does not know about the size of the main memory. So let us assume that this load instruction access the main memory DRAM with this address, and then this is another load instruction from the different application. So let us assume this different application also access the 0x0010. So what's the problem? If different applications access the main memory using the real memory address, then when the program is compiled by compiler, then the compiler needs to know the location, the address, the real physical address of this target data. But it's not possible because we don't know, the compilers do not know the target, do not know about the target systems. So what does that mean? So actually, the operating system and computer hardware just provide another abstraction level called the virtual memory. So which means that instead of accessing the main memory using the real address, which is the physical address, then this load instruction just access the main memory with the fake address, is called the virtual address, like 0x0010. But this address is the virtual address. And then when the real DRAM is accessed by this load instruction, then we need to translate. So we need to map this virtual address to the real address, because the data really exists in the real memory. It's a physical memory, it's a physical DRAM. So software access the data with the virtual address, but we need, actually the computer system needs to provide the real data which exists in real physical memory. So which means that this virtual address is translated into the physical address, and then we need to access the data in the DRAM, is the main memory, with the physical address. Also, then, so this, if this address is the same, so this is the different, the load instruction from a different application, and then let us assume that the virtual address is the same, like 0x0010. But we already know that so these are different applications, so which means that the data are different. So which means even though the virtual address is the same, the data are different. So which means that this different data exist in the DRAM with the different real address. So which means that different physical address. So this virtual address is translated into different physical address and then access the different location in DRAM. So what does that mean? Actually, software so I said that operating systems and computer hardware like computer systems provide another abstraction level to software. And then this abstraction level is the virtual memory. So which means that software, when the software is designed, then we assume that this software can access very large memory. But this is the virtual memory. Also, we assume that the target hardware has enough number of cores that can run this software. So this means that so infinite processor cores. Okay. So for example, so let us assume that your system has 4 GB of main memory, but operating system or the so when a software is designed and then we operating system just provide that you can access the 4 TB of memory, for example. It's a very large memory, but the target our system has only 4 GB of memory. Okay, so which means that when a software is designed, we don't need to consider about the limited size of the main memory of the target system. So we can use the very large memory, but when this software, the compiled binaries are run on the target system, then operating system or some computer hardware just manage the which data, so the location of the data. Okay, so this is the concept of virtual memory. Okay, so which means so software just access the data with the virtual address. So which means that the software access the data with the not real address, is a virtual address. Then this virtual address is translated into the physical address. So which means that it's the real address that points the location of real data in physical memory, like real memory. Okay, so without this physical address, then the hardware access the RAM. This is the concept of virtual memory. So you may be confused because so until now, so I explained that the load instruction, when the load instruction, what's the purpose of load instruction? The purpose of load instruction is to transfer data from main memory to the register file, right? But so we can say that when the load instruction is executed, then this address handled by this load instruction is virtual address. The purpose of the load instruction is the same. So, which means that the purpose of the load instruction is to transfer data from main memory to the register file, right? The purpose is the same. Actually, the meaning of the load instruction is the same, but you need to think that address handled by this load instruction is the virtual address. So which means that addresses handled by software are virtual addresses, like the it's a very large, the addresses for very large fake virtual memory, but we need the software runs on the real hardware. So software runs on real world. So this virtual fake address need to be translated into real address in order to access the real data in real physical memory. Okay, so hardware supports this translation. Okay, so this is the concept of virtual memory. Understand? So, so actually, the original purpose of a virtual memory system is to use the main memory, the main memory which use the DRAM as a cache for storage. What does that mean? So actually, the old computer systems equip very small main memory, right? Because the DRAM was so expensive. So DRAM is also expensive currently. So it's more expensive than the storage devices. But in old computer systems, so DRAM was very, very expensive. Also, the DRAM size was very small. Okay, right? So originally in the old computer system, DRAM size so small. Also, DRAM was very expensive. So its memory is small and the memory is expensive, but we want the large space for our data. But we don't want sacrifice performance of our computer system. Then available idea is caching, right? Why do you use cache memories? Because even though the DRAM is very large, but DRAM is very slow. So we want to store the large amount of data in our main memory, but this main memory is very, very slow. So we have the processor has cache memories or cache hierarchy. It's the size of the cache memory is small, but it's fast, right? So the same concept can be applied to the RAM, the main memory of the computer system, and storage devices. So which means that a processor can use DRAM as a cache, and then we can use the large storage space like the hard disk drive spaces as the memory space. And then for the purpose of this some caching up, so in order to use the DRAM spaces as the cache space for storage device, then virtual memory concept was invented. So what does that mean? Like this. So this is the virtual address. So which means that to the software, the computer hardware or operating system provide a fake large memory space. So even though the real physical memory size is smaller than this virtual address space, so virtual memory space. So, but to the software just see the very large virtual memory space. And then when this virtual memory is mapped to the real memory, so in reality, our world is not perfect. So it means that actually the size of the physical memory is small. So it's a physical memory. Then how can you provide the large space for the data of software? So we can use the spaces in hard disk drive or any storage device as the additional space for this virtual memory, right? So this is some data blocks in hard disk drive. So to the software, then you can say that, oh, you can use this large memory space, but in reality, some part of this virtual memory is mapped to the real fast memory, like real DRAM, but another part of this virtual memory is mapped to the storage space. So storage space in slow, very, very slow storage devices. Okay, this is the original purpose of virtual memory. So, which means that some part of the data, or some part of data is mapped to the physical memory, like DRAM, but some part is mapped to the space, the storage space in the hard disk drive. Okay. So the first purpose of the virtual memory is to use DRAM like a cache. Okay. So which means that when the load instruction access this data with the virtual address, then we translate this virtual address to the physical address, then we can find that, with this physical address, then we can access the real data in physical memory, DRAM. Then we provide the computer systems, provide the data with the physical address. Okay. And how about this? The software access this data with the virtual address, but this data is not mapped to the physical memory because of the limited size of the physical memory. This data can be found in the storage devices, like here. So in this case, then this event is called the page fault, right? Then the computer hardware, actually operating system, read this data block from the hard disk drive, then move this data to the main memory. And then existing, so we can use the DRAM like a cache. Then how about the existing data? If this existing data, because this existing data is evicted from the DRAM, then this DRAM data is moved to the hard disk drive, and then the operating system fills this block from the hard disk drive, right? And then operating system remapped this virtual address to the new physical address here, and then access this physical memory with the physical address. So when page fault happen, then it will take very long time, right? So it is because the first we need to access the hard disk drive, and the hard disk is very, very slow. Okay, so actually we handle page fault like an exception. Okay, it's an exception because it's very rare case. So this is the original purpose of the virtual memory. So actually in the old computer system, the DRAM was so small, like the 640 kilobyte, right? It's less than 1 megabyte. The size of the DRAM was smaller than 1 megabyte. It's less than 1 megabyte. So like which means that the operating system, also the normal applications, need to use the 640 kilobyte of the main memory. It's very, very small. So and then the solution is that, we can use the large space in the hard disk drive. So even in the old computer system, the size of the hard disk drive was also much smaller than the today's hard disk drives. But the size of the hard disk drive is relatively larger than the size of the DRAM. So which means that, so even though this computer system has only the 640 kilobyte of the main memory, but you can use this very large hard disk space as like the memory. Okay, so this is the original purpose of a virtual memory. Then how about today's computer system? So even though the size of the main memory is smaller than the size of the hard disk drive or solid state drives, so the size of the main memory is very large in today's computer system, right? It's usually normal computer systems have 4 gigabyte of the main memory also, and then many computer systems, such as even the very high-end smartphones, have 6 gigabyte or 8 gigabyte of main memory, right? So, but we still use virtual memory. Even though the size of the main memory is increased recently, and which means that we use very large main memory, we still use virtual memory concept. Why? Then, so today's computer system, why do we use virtual memory? As I explained in the beginning of today's class, we just provide some imaginary memory space, like fake space, and then also with the operating system or the computer hardware provides the imaginary CPUs, like a number of cores, to the software. Actually, there are many benefits benefits from virtual memory. So which means that, first, think like this. So you are writing a certain code. So you are writing you are designing a software. Then let us assume that we need to manage the real location of the data in the physical memory. But the target, if we just actually our compiled binaries can be executed on the very low-end computer system. Also, our same binaries can be executed on the high-end computer system. So we don't know about the target computer system when we design software, right? So let us assume we can access the data directly with the physical address. Also, another difficult thing is that, so when a binary is executed on computer systems, many other binaries or many other threads can be running on the same computer system. So for example, so we can check how many processes and then how many threads are running on our computer system. So which means that if we press the Control Alt Del on the Windows operating systems, then we can check the running processes on our computer system. And then usually the number of running processes are hundreds or even so actually many. So like the 100 processes are running on our computer systems, right? Also, we can, Linux operating systems, we can use tab command. Then we can check the running processes on this Linux operating systems. So what does that mean? Actually, when an application is launched on the computer system, actually this launched processor is one of running hundred of processes. One of hundred of running processes. So we don't know which processors are running along with our own application, right? Which means that when the software is designed, we don't know the environment, the running environment of the target computer systems. It's very, very, very difficult. So actually it's not possible. So which means that with the load instruction, if this load instruction access the data with the physical address, then a software cannot manage these addresses in the physical memory. Okay, that's why currently we use virtual memory concept, even though many computer systems equip very large memory. So the original proposal of a virtual memory concept is to use DRAM like a cache, but today, in today's computer systems, we still use virtual memory concept because we just provide the very simple abstractions, so very simple and very simple abstractions to the software level, and then we can design a software very easily. But this virtual space is translated into the physical memory space using this virtual memory concept, and then we can simplify the design of a software. But hardware and the operating system, this hardware and operating system needs to provide the translation step for virtual address to the physical address. Do you understand? So it is because operating system just manages the software, how many softwares are running on this current computer system. Also, the operating system manages the resources in computer hardware. Okay, so which means the operating system knows the current running environment, so current hardware resources and then current software running situations in the target computer systems. Okay, so operating system just provides the virtual memory space to the software. Also, the hardware supports this virtual memory operations. Okay. So you may be confused that so software just with the instruction like the load instruction just access some fake memory like it's a fantasy world actually. It's a fantasy world. So it's a fake memory. So it's unreal memory. So actually this load instruction access the data in the fake memory or fantasy memory. Okay. So actually, so this is the original purpose of the virtual memory. As I explained, the original purpose of the virtual memory is to use main memory like a cache for the storage devices. But actually, these are some purpose. These are the real purpose of virtual memory concept. Okay, so many programs, many processes share the physical main memory, and then actually it's not possible to manage these physical addresses of each application when a software is designed. So actually, operating system manages some memory spaces in the real physical memory, and then operating system just change the mapping informations for each running running process, right? So then operating system can manage the protection or sharing between different processes. Okay, so this becomes the main purpose of virtual memory concept in current computer systems. Okay, so in order to provide the virtual memory concept, then operating system and computer hardware, the hardware need to provide the translation from virtual address to the physical address. Okay, so for example, so like this. So the load instruction is access the memory, like load x1, 0, x2. Oh, this is the address, but I said that this address is the virtual address. So this virtual address is given to a hardware or processor. Then, we need to know the real address of this load instruction or this target data, right? Because the target data exists in real memory, okay? So real physical memory, but this load instruction accesses this data with the virtual address. So in order to figure out the real address of this target data, not this is target register, target data, then this virtual address need to be translated into the physical address. So which means that, this is the virtual address. This virtual address is mapped to the physical address here. Then a processor need to access the DRAM with this physical address and then return data to the load instruction, right? So for example, this address, as I mentioned, this address is 0x0010, and then this address is translated into the physical address like the 0x1020, this. And then the processor accesses DRAM with this address, and then read data from the DRAM. So we can read data, and then this data is provided. So in order to use the virtual memory, then this virtual address should be translated into the physical address. And then this translation is supported by operating system and hardware. Okay, but then how can you translate this virtual address to the physical address? So, and then we learned that the most of address is byte address. So which means that 1 byte is assigned to the address 1 of the instruction. So, okay, right. So which means that for every address, then we can translate this virtual address into the physical address. So what does that mean? So like the 0x010 is mapped to the 0x1201 or 1020, and then 0x110011 is mapped to the 0x0031. 0x0012 is mapped to the 0x0062. Blah blah blah. That can be possible because the address is byte address, but this is not practical, right? So for this translation, we require translation information, which means that the mapping information, and in order to provide the mapping information to every byte address, then this mapping information will be very huge. Also, it's not practical, right? Because the usually the size of a cache block is equivalent to the size of the burst read in main memory, and then this burst length of the burst read size to the main memory is about 64 byte. And then so which means that if we just use the different byte address, the different byte address for the physical address, then it will be very impractical. So put the virtual address translation to the physical address, then we just translate the large chunk into the large chunk of the virtual address into the also the same size of a chunk of physical address. So which means that we can translate the 4 kilobyte of size of virtual address block into the 4 kilobyte of physical address blocks. It's a 4 kilobyte. The size is it's rather larger than the byte size because it's a 4 kilobyte. And then if we manage the mapping information with this large block chunk, then we can more easily manage this translation information from virtual address to the physical address, right? So this chunk is called the page. Okay. So when a virtual address is translated into a physical address, then we translate in the size of a page, and usually the size of a page is 4 kilobyte, which occupies the 12 bits of the 12 bits in lower memory address, right? So actually, when a virtual address is translated into a physical address, these 12 bits, lower 12 bits are not translated, right? Because we translate the 4 kilobyte of page, a virtual page number into the physical page number. So this lower part of the virtual address is not translated. Do you understand? We just translate the upper bit of the virtual address into the physical address. So this, when the page size is 4 kilobyte, and then this page occupies the lower 12 bits of the virtual address, and then these lower 12 bits are directly copied to the lower 12 bits of physical address. Instead, the upper part of the virtual address, so which is called the virtual page number, it's VPN, and then this VPN is translated into the physical page number called the PPN. So in this example, the virtual address space has the 48-bit addresses. So, and then among these 48-bit address, lower 12 bits are directly copied to the lower 12 bits of the physical address. So then this upper part has 36 bits. These 36 bits are translated into the physical page number. And then how about the size of the physical address? So in this example, the size of the physical address is the each 40 bits. And then also this is the 12 bits. So which means that physical page number occupies 28 bits, right? So which means that 36 bits of VPN, the virtual page number, is translated into the 28 bits of PPN, the physical page number. So you can find the virtual address has the more address bit. Is it because we provide the very large? It's a fake, not real. Just both operating system and hardware provides the very large virtual memory space. So which means that software can access any data, not any data in practically, but software can use this, think that, oh, I can access this very large virtual memory space. So we don't, and then software does not consider about the real size of the physical memory. So software just access the virtual memory space. But this VPN is translated into the PPN, which has smaller number of bits, like 28 bits. It is because the real memory size, real physical memory size is smaller. Then what is the real size? What is the size of the physical memory in this case? So physical address has 40 bits, right? Then what is the size of the physical memory? It's 40 bit. It's 1 terabyte, right? 10 is kilo, 20 is mega, 30 is giga, and then 40 is tera, right? And then the physical address has 40 bits. The size of this physical memory is 1 terabyte, right? But what is the size of the virtual memory? So 48 bits. So 40 is tera, which means 2 to 8 terabyte, which is 256 terabyte. It's very large. Obviously, the 1 terabyte of the main memory is also very large. So usually the physical address has smaller number of bits in really usually. But if a processor provides the 48 bits of the virtual address for bits for virtual address, then which means that the virtual memory size is 256 terabytes, ridiculously large. Okay, but the real memory size is much smaller, so 1 terabyte in this example. So usually we have a smaller memory like the 16 gigabyte for the high-end laptop. Also, we usually have 4 gigabyte of the main memory. So which means that if we if our computer system equips 4 gigabyte of main memory, then physical address, the number of bits in a physical address is number of bits, it's 32 bits, right? It's a 4 gigabyte. So this is the virtual memory concept. And then in order to translate the virtual address to the physical address, then we use the very large chunk called the page. Okay. And then the virtual address, actually, when a virtual address is translated into a physical address, virtual page number is translated into the physical page number, PPN. And then the lower 12 bits is called the page offset, because the size of a single page is 4 kilobyte. So page offset is copied to the page offset part of the physical address. That's how the virtual address is translated into a physical address, right? So then I also explain about the page table. So page table means that the virtual address, when the virtual address is translated into a physical address, but this target data. The target location is in the storage. Okay. Then it means that, with this virtual address, we need to access this data in the storage. So, and then as I explained, this event is called page fault. So which means that page fault means that the target of virtual address is found in storage. That is the page fault. So which means that the target of virtual address is not found in main memory. It's page fault. And then I explained that. So in this case, when page fault is detected, it's a page fault occurs. This is the exception, kind of exception. So which means that when exception is detected, then the processor needs to call exception handler. Then this code is provided from operating system. Then when page fault happens, we need to transfer the requested data, actually page data, so 4 kilobyte. So we need to transfer page data from storage to main memory, right? So in this case, when page fault happens, then the operating system needs to access data on hard disk drive or SSD, so solid state drives, and then it'll take a very long time. Okay, so the exception is detected in this case. So and then page fault handler is called by the code, and then the data is transferred to the so data on this hard disk drive is moved to transfer to the main memory, and then the existing data is also transferred to the hard disk drive. And this process is called swap. Okay, so and then this process, the data is transferred from hard disk drive to main memory. It's called the swap in, and then this process, the page data is evicted from main memory to the hard disk drive. This process is called swap off. Okay, the swap means that the data is changed. So data between main memory and hard disk drive are changed each other. So this why this process is called swap. Okay, so data is swapped in the main memory, and then this translation, the translation information is updated, and then with the updated translation, then the access the updated the main memory with the updated physical address. So which means that when the load instruction is executed, like x0, 0, x2, and then page fault happens. Okay, and then exception handler is called, and then some swap process is swap process is performed in the computer systems, and then the translation information is updated to the target memory space for the swapped in page. Then this load instruction is restarted, right? That's why the page fault is a kind of exception. Okay, and then page fault is handled by exception handler. It's a software code, right? So this is the page fault. Then how about, then we need to translate the virtual address, actually virtual page number, to physical page page number, the VPN to the PPN. And then how can we manage this mapping information? This mapping information is managed by actually operating systems, because operating systems know the current status of the computer system, entire computer systems. And then when a process is launched, so which means that a binary is executed, then operating system assigns this mapping information, like, and then this mapping information to the launched software, launched process, and then this process, like the binaries, can be executed by a processor. And then this information is the mapping information. This mapping information is managed in page tables. Now, how can we manage the mapping information? Actually, we need to translate the virtual page number to physical page number. So which means that in this example, the virtual page the size of the virtual page number is the 36 bits. So which means that is the 36 bits of the virtual page number is mapped the physical page number. For example, 0x000 is mapped the 0x100, 0x001. It's the VPN. And then this is mapped the 0x110, and then 0x112 is mapped to 0x210, something like that. So actually, this information. So these page tables are managed by operating system, so which means that a processor is launched in a computer system, then the page tables are made by operating system, and then this page table is assigned to newly launched process. Okay. So it means that with the VPN, and then it's kind of a data structure. So which means that it's like so operating system can make those array, like the page table array, like PT0 to blah blah blah, a very large number, and then we assign the PT0. We store the PT0 and 0x100. Because the VPN is the 000. So which means that we access the page table entry with the VPN, virtual page number, and then VPN includes the target page physical page number, like 0x100. Do you understand? So which means that if we provide this VPN, then the target element is read from this array, page table array, then we can get the physical page number assigned to this element. Okay. It's a simple. So I explained how the virtual page works simply. So it's a simplified version, not real virtual page data structure. So actually, in a virtual page entry includes the many other informations, such as the some permissions, and then attributes such as the read only or write. Also, this virtual page entry includes the notifications, so which means that the target page is updated or not. So many other flags are also stored in the entry of the virtual page. So, and then this virtual page entry is managed by operating system. Okay. So, and then let's see how the virtual page numbers are translated into physical page number. So this is the virtual address, and then and then let us assume that the page size is the 4 kilobyte. So it means that the page offset occupies the lower 12 bits of virtual address, and it's the same to the page offset also occupies the lower 12 bits of physical address. And then this page offset part is directly copied to the page offset part of the physical address. And then this is the virtual page number, and then this is the page table. So in the processor, processor stores the page table register, and then this page table register points the first address of page table. Okay, because the page table is managed by operating system, which means that actually the page table is the software data structure, as I explained. So it's like a PT, we can access the element of the page table with the virtual page number. Okay, like this. So real hardware, then in order to access the page table, then we need to know the pointer, the address of the page table pointer, and then so which means that the page table register stores the pointer to the page table. Okay, so when the virtual page number is given, then this virtual page number needs to be translated into physical page number. Then we need to access the page table with this pointed by page table register. It's a software data structure. So then if this virtual page number is 0x, so 0x004, then we just access the page table 4. Okay, and then this page table entry includes the physical page number, so 28 bits. Also, this target page table entry includes the many flags, so many attributes or some control bits for page table target page. So this page table entry is accessed, then we can get physical page number. So virtual page number is changed to the physical page number. So which means, and then page offset is just copied. Then we can get physical address. Okay, so this is the real address for target data. Do you understand? So that's how the VPN, the virtual page number, is translated to physical page number using page table. Also, the target page can be found in the physical memory like DRAM, or the physical page can be found in the disk storage. So we can distinguish these different locations like between physical memory and disk storage with the valid bit. So which means that if the valid bit is 0, so which means the target page exists in storage. Okay, so this is the page fault. Okay, and then actually, so which means that when the virtual memory concept is that we can use the physical memory, the DRAM, as the cache. So which means that we require the replacement policy. So which means, so when a cache miss occurs, then we need to replace the cache blocks, right? Set associate. So if this happens in cache, then we need to replace the target cache block, right? And it's the same to the virtual memory. Okay, so virtual memory, so we can use this DRAM like a cache, then we can apply the RLU. Okay, so this is the mapping table, and then based on the mapping table, then the target page can be found in memory or data. And then cache miss means that it's a page fault. It's page fault is like the cache miss. So when cache fault, the page fault happens in virtual memory, then we need to replace the pages. So which means that when this data is swapped in to the main memory, then we need to decide where to store this target page in main memory. Okay. Also, which data is evicted from the main memory. Because we use the main memory like a cache, then we can apply the RLU policy, like least recently used replacement. But the main memory size is relatively large. It's very actually much larger than the real cache size. Also, this replacement policy is applied to cache, then actually the replacement policy can be applied to the several, like for the 8 ways set associated with cache, then we can apply the replacement policy, RLU replacement policy to 8 different cache blocks, right? But the memory is actually, so it's not practical to apply the very precise LRU algorithm for this page replacement policy. Okay, so actually when the page table is replaced, then we check. So actually we check the access bit, so reference bit. So and then this reference bit is periodically cleared by operating system, and then we just select some pages whose reference bit is 0 from the main memory as the evicted pages in main memory. Okay, so which means that we just apply the very simple replacement policy. Okay, and then also storage is very slow, right? So which means that the write-through policy is impractical because the storage is very slow. So we use the write-back policy for virtual memory. Okay, so which means that the page table entry also includes the dirty bit. So which means that if the data is updated to the tag pages in main memory, then we can check the dirty bit in the page entry. Then we can check if the target page is updated or not. Okay. So I explained about the virtual memory and then how our page table is used for VPN to PPN translation. And then this page table is managed by operating system. It's a software, and then so which means that to access this page table, then usually this page table is found in main memory. So this page table register has the address, the pointer to the page table, which means that page table actually exists in main memory. So what's the problem? So when the load instruction is accessed, then this is like, I will explain here. The load instruction is accessed like x1, 0, x2. Oh, this is the virtual address. And then in order to access the target data, which is in main memory, then this virtual address needs to be translated into the physical address. The problem is that for this translation, we need to access the page table. And then where is the page table? In main memory. So, and what's the problem? In order to get this translation information, mapping information from page table, we need to access main memory. Problem? Performance. Why do you use cache? Because main memory is slow. Then, but problem is that in order to use virtual memory, and then for every memory reference like load instruction or store instruction, then we need to access main memory for getting translation information from virtual table, a page table. It's ridiculous. So the processor supports the cache for page table. And then this cache for page table is called TLB, translation record side buffer. So I will explain about the TLB in the next class. Okay. So in this class, we learned about the virtual memory concept. And then actually the virtual memory was invented for using main memory like a cache, but virtual memory is still used for the modern computer systems which have large main memory, because operating system and hardware just provides the abstraction of the virtual memory, the fantasy world, to the software. So which means that the software does not consider about the real location or real address of the physical data. Okay. So and then I will stop here. And then so in the next cycle, I will cover the TLB, the translation record site buffer. And then I will conclude the chapter 5, the memory hierarchy. Okay. Thank you for attention. And if you have any questions, then please post your questions on Piazza. Thank you, and see you in the next class via Zoom. Okay, bye.